First and foremost, my sincere thanks to the organizers of this session, Chris Katibis, Karen Lupo, and Dave Schmidt, as well as the organizers of SAfA for making this gathering possible. Our presentation gives you an inside look into our paper published earlier this year, proposing a population collapse in the Congo rainforest from 400 CE. The Bantu expansion is generally regarded as the most significant migration event in sub-Saharan Africa, synchronous with the introduction of a sedentary lifestyle and characterized by the production of pottery. It is commonly assumed that the current-day geography of Bantu languages reflect the original migration of Bantu speech communities, and multiple studies attempted to retrace this expansion. But one persistent question is to what extent present-day data, particularly linguistic evidence, still reflect any initial expansion of material, cultural, or communities themselves. All these studies simply assume a continuity that is sometimes rather wishful thinking than empirical fact. The notion that in Central Africa the early and late Iron Age were separated by a period of population collapse has been considered at least since a paper Pierre de Marais presented at a conference in France in 1998. Later on, it has been considered for southern Cameroon and Gabon by Richard Slisley and others in multiple papers, focusing on the empirical interpretation of radiocarbon dates from only a limited pool of dates allowed others to attribute the results to a mere research gap. While the results of our study are based on multiple lines of evidence, due to time constraints and the scope of this session, I will focus on the evidence derived from radiocarbon dates and pottery inventories. We conducted an integrated analysis relying on quality screen archaeological C14 dates from 7 countries in Central Africa in order to build a comprehensive supra-regional analysis of well-dated archaeological records. We compiled a dataset of 1444 C14 dates from the study area that are younger than 2000 BCE. We included information on the archaeological assemblages each date was sampled from, like pottery, metallurgical objects, including iron slag, and or edible fruit remains, typically charred endocarps of Elaeus guineensis. This allowed us to evaluate the reliability and relevance of individual C14 dates with regard to our study, taking into account the interpretation of the original author and the results of subsequent analyses. All available context information was then condensed into a transparent classification system for each C14 date as summarized in the table on the left. While the following analysis was based solely on radiocarbon dates assigned to class 1, 1100, because they are reliable and unmistakably associated with human activity due to them originating from archaeological assemblages containing pottery or metallurgical remains and or abundant edible fruits, I want to highlight a case in which dates have been assigned to class 3A, presumed lab errors. In total, 121 C14 dates in our dataset were produced at the Niedersächsisches Landesamt für Bodenforschung at Hannover, Germany, during the 1980s. During that time, this laboratory faced a substantial problem concerning the reproducibility of C14 dates and potential errors due to the use of acetylene as counting gas as published by Guy in 1990. Doubts on the quality of Hannover dates were first raised in the late 1980s by Manfred Eggert, but a critical analysis of their reliability in the context of the associated archaeological finds has been conducted only by Hans-Peter Wotzka for material remains from the Inner Congo Basin. We incorporated the conclusions of that study in our C14 database by assigning these dates to class 3A and excluding them from the main analysis. However, other archaeological C14 dates produced at Hannover during the 1980s, mostly from Cameroon, Gabon, and the Lower Congo, lack a detailed discussion of the reliability, and therefore we have no a priori reason to exclude them from our analysis. Moving on, with pottery being the only constant find category within the region, we focused on compiling a comprehensive database of all well-described and directly dated pottery groups or styles in the Congo Basin. The temporal distribution of all these groups can be seen in the figure on the left. Circles represent the highest probability calendar age of each pottery linked C14 date, and the intensity of gray shading is proportional to the sum probability of the calendar age windows of all pottery occurrences per type. You can already see that a certain pattern emerges. In most regions, the earliest pottery dates into the first millennium BCE, but toward the mid of the first millennium CE, these sequences end. Only ceramics from the beginning of the second millennium CE can be found again. In order to further explore this pattern, we compiled region-specific trends in human activity based on the sum probability distribution, or SPD, of archaeological C14 dates from the Congo Basin over the past 4,000 years that you can see on the right. The gray envelopes represent the 95% uncertainty envelopes of 100 simulated SPDs generated by randomly picking an equal number of radiocarbon dates from the cross-regional dataset, which you will see in a moment, to highlight the regional specific trends shown by colored lines. You can see that, for example, the SPD from southern Cameroon surpasses the gray envelope in the first millennium BCE, meaning that the pattern observed here is significantly more prominent than the cross-regional trend. But most importantly, in nearly all regions, the regional SPD follows the same pattern that we saw in the chronologies of the pottery groups already. At the mid of the first millennium CE, the probabilities dropped distinctively. Based on these regional SPDs, we calculated the posterior probabilities for all calendar years using the INCAL 20 calibration curve. Similar dates from the same site are grouped together in bins in order to compensate for investigator biases. This bias occurs when multiple radiocarbon dates have been performed on a single archaeological feature, for example, a single refuse pit, and some or all of these are within the same age range. The so-called empirical sum probability function is calculated from the binned and calibrated C14 dates. To offset variability created by the calibration process, the SPD was smoothed using a moving average of 60 years. One can already determine two phases. Dates from the early Iron Age typically range between the first millennium BCE and the first half of the first millennium CE, while the late Iron Age only starts in the second millennium CE, leaving a gap in between the two phases. To visualize data variability, we calculated a composite kernel density estimation from 500 sets of the calibrated ages of 675 randomly sampled C14 dates, corresponding to the number of bin dates. This alternative approach highlights the mathematical uncertainties embodied within the summing up of the vast amount of probability functions. As you can see, it corroborates the general pattern. In order to demarcate the periods with higher and lower human activity, we compared the observed or empirical SPD with hypothetical models of uniform, linear, exponential, and logistic population growth. This approach uses averages over 1,000 Monte Carlo simulations drawn from our database. The 95% confidence intervals per calendar year of these averages are shown as gray bands in the figure on the right. This allowed us to identify periods during which the empirical SPD significantly exceeds or falls short of the theoretical models. Such periods are considered periods of more or less intense human activity, respectively, and visualized by blue and red shading. You can already see that the pattern observed within the empirical SPD results in a very similar phases of more or less human activity in all four model tests. Most importantly, all four models indicate a significant drop in human activity in the second half of the first millennium CE. In order to better characterize the results of these tests against hypothetical growth models, we overlaid them within a single figure, here shown on the left. The darker the color shading, the more reliable the results at the period of more or less intense human activity was detected in multiple growth models. In this figure, we included a logistic growth model, as it is probably the pertinent in the context of the Bantu expansion, which is often discussed as a large-scale and exceptionally rapid process followed by a continuous presence of Bantu-speaking people after the initial expansion. To better characterize the magnitude of demographic change during these phases, we calculated the rate of change in the SPD. Changes exceeding the first quartile of all positive growth rates are marked as expansion. Similarly, we defined an SPD declining as collapse, where the rate of change is lower than the first quartile of all negative growth rates. This results in the demarcation of phases shown immediately above the SPD. These results enabled us to comprehensively and statistically assess the C14 dates at the scale of the entire Congo rainforest. In a nutshell, all four models predict a significant setback in radiocarbon dates and thus human activity between 600 to 1000 CE, preceded by a collapse starting around 400 CE. We also considered similar data sets from the southern Congo Basin woodlands, regions I and J, and Bioko Island in the Gulf of Guinea, region K, two areas adjacent to the present-day forest. In the woodlands south of the Congo Basin, most dates originating from the Upemba Depression, the period of elevated human activity starts only at about 600 CE. This is considerably later than further north and correlates with the period of less intense human activity described before. The second pillar of our analysis covers the temporal distribution of recognized pottery groups in the Congo rainforest and shows a marked repetition of the same two-phase settlement pattern during both the early Iron Age and late Iron Age. Each expansion phase, here seen in light gray bars, is characterized by an initial low but increasing number of pottery groups, seen in panel A on the left. These pottery groups tend to be stylistically homogeneous across large numbers of sites, as can be seen in panel B, and consequently tend to have a large distribution area, shown in panel C. In contrast, the subsequent periods of high activity in dark gray bars are characterized by a large number of pottery groups, of which many are found at only a few sites, and consequently have a smaller mean area of distribution. This is indicative of a regionalization process. The two-phase pattern, and in particular substantial changes within the characteristics of the ceramics occurring in between the phases, can also be seen within the regional archaeological record itself. In the inner Congo Basin, the initial expansion period is characterized by the dominance of the well-known Mbonga group, which spread over a vast area within less than 200 years. It is characterized by flat-based vessels decorated with grooves, as well as rocker zigzag on the lower half. Over these subsequent 500 years, it morphed into multiple distinct styles, whose unique characteristics in terms of vessel shapes and decorations all disappeared during the collapse period. Then, from about 1000 CE, the previously unknown widespread Bondongo pottery emerged, which in turn split into regional specifications within the next century. With it starts a predominant round-based vessels and a nearly omnipresent decoration technique, the so-called manfal. A similar pattern is found in Gabon, where the widespread Okala pottery coincides with the early Iron Age expansion period. During the subsequent regionalization period, this widespread pottery group fell apart into the Okanda, Oveng, and Otumbi groups, each showing only very local distributions. Also, the ceramic sequence within the region close to the mouth of the Congo River show an intermission. A conservative estimate places the earliest ceramics in the region into the 4th century BCE. Multiple subsequent pottery styles, some of them only separated based on research tradition, show an evolution of characteristics. This early Iron Age evolution ends toward the 5th to 7th century CE. The younger part of the sequence, covering the late Iron Age, has been the focal point of the Congo King project and is now considerably better known. The pottery of this phase show no connection to earlier groups. In the eastern or upper Congo Basin, even a shift in pottery technology was recorded, as early Iron Age pottery technology was markedly different from that of later pottery groups. The vessels of the early and middle phase were produced by drawing of a ring technique and decorated using grooves and rocker zigzag, similarly to the contemporaneous pottery further west in the inner Congo Basin. Later ceramics are shaped by pounding in a concave mold and roulette decoration emerges. These distinct breaks in material culture confirm the existence of two clearly distinct periods of pottery production in that region. After laying out our arguments derived from multiple lines of evidence that are including a reconstruction of demographic patterns with genetic evidence, we offer possible drivers for the population collapse. In order to account for this collapse to be present in such a vast area, sites or villages would need to be well connected. While within comments to our paper we saw that there are some misconceptions stating that population density in the early Iron Age were low and the villages probably widely spread out, on the contrary, conducting a connectivity analysis of georeference sites with well-described pottery styles shows that the median distance between a site and its 4 nearest neighbors within the same pottery style is only 35 kilometers, suggesting a relatively dense network of well-connected villages. Today, the vast network of tributary waterways in the Congo River basin constitute a major transportation system connecting thousands of villages, and likely it had the same connective potential in the past. Finally, I want to broaden the scope a little bit and look outside the box of our study area. A very well-managed database of radiocarbon dates from southern Africa was published recently. Comparing the SPD from those dates show an empirical curve that largely matches a hypothetical exponential growth model. For Eastern Africa, there's currently no published database on radiocarbon dates available, but during personal communication, Stephen Goldstein pointed at some very intriguing results using a similar approach that he and his team are currently writing up for publication. Furthermore, we might also want to consider reviewing datasets from similar biomes. Earlier this year, Manuel Arroyo Galim and Philip Rearis published a paper on the carrying capacity of pre-Columbian populations in the Amazon. They also made a comparison with our results in a later talk. What is interesting is that the onset of intense human activity and sustained population growth in the Amazon is marked by a shift from exponential to logistic growth occurring around 200 BCE. This is not much later than the initial expansion phase we found for Central Africa. Within our study, we not only made a specific effort to produce a database that is comprehensible, but also we made it publicly available. Actually, the database itself, called ADRAC, or des Archives de datation radiocarbon d'Afrique centrale, is publicly available since 2016 already. There's also a front-end web page that can be used to search for specific dates. While ADRAC will be used to add new dates, the data on pottery groups we compiled for our paper will be curated in their own little archive. But again, not only the data are available, but also the software code that we wrote in order to perform our analysis. Thus, if you have any more detailed question on what we did, I welcome you to check out the repository. Finally, to bring this presentation to a close, I would like to reiterate the two main results. First, the combined archaeological evidence supplemented by human genetics show that the boom and bust pattern in the SPD of archaeological C14 dates does reflect past fluctuations in the overall density of the human population inhabiting the Congo rainforest. And second, until now, the dispersal of Bantu-speaking communities in the Congo rainforest has tended to be seen as a single and long-term continuous macro event. Our results show that any initial wave of early Iron Age communities largely vanished from the entire Congo rainforest region by around 600 CE, with a persistence of only a very few scattered population. And with that, I thank you very much.